Now let us try to find center of mass for another object, which is a right angle triangle. Suppose if this is a right angle triangle of side A, base A and height B, if this is a right angle triangle of base A and side B, then how to find the center of mass of this triangle? Suppose mass of the triangle is M. Mass of the triangle is M, and you choose the axis like this: x axis, y axis. Choose the axis like this, and on the triangle choose an element here of thickness dx. So at a distance x, you have selected an element dx whose height be y. So height of this strip that we have selected is y and its thickness is dx. Then the area of the element that we have selected will be equal to y dx. Area of the element selected is y dx. Then dm, mass of the element that we have selected, dm will be equal to area into mass per unit area. Y dx, area of the element into mass per unit area means total mass of the triangle is m by area of the triangle is half AB. That will give you mass per unit area of the triangle. Total mass of the triangle by total area of the triangle will give you mass per unit area of the triangle. So that into area of this element will give you dm. This is equal to y dx into 2m by AB. This is dm. This is dm. Now let us apply the formula. Y center of mass is equal to 1 by m integral let us try to find the x coordinate first. Afterwards we will see what would be the y coordinate. xcm is equal to xcm will be equal to 1 by m into integral x dm. This is equal to 1 by m integral x into dm will be equal to y dx into 2m by AB. So this is mm gets cancelled. You are left with 1 by AB into integral 2 by AB into integral xy dx. So here center of mass x coordinate by formula is 1 by m into integral x dm. X into dm is mass of this element, which is equal to area of the element into mass per unit length. That will give you y dx into 2m by AB. For dm you write this value here, y dx into 2m by AB. Then simplify, m gets cancelled. What you are left with is 2 by AB into integral xy dx. Here we have to eliminate y from the triangle so that you can have a function only in terms of x which can be integrated easily. Now from this diagram, y by x is equal to b by a, or y is equal to bx by a. You can write y is equal to bx by a. From this triangle and this triangle are similar, so y by x is equal to b by a. So y is equal to bx by a. Then this can be written as 2 by ab into integral y is equal to bx by a means x into bx by a dx. So x, it is a function of x whose value lies from 0 to a. So limits will become 0 to a. Now xcm will be equal to XCM will be equal to 2 by AB into B by A comes out, B by A into integral x square dx, integral x square dx from 0 to A. So, XCM is equal to BB gets cancelled, 2 by A square, integral of x square dx is x cube by 3, limits from 0 to A. That would be equal to 2 by A square into A cube by 3. This gets cancelled. This is equal to 2A by 3. So, x center of mass for this triangle is 2A by 3. In the same way, you can also calculate y coordinate of center of mass for this triangle, which is not 0 here because center of mass will lie somewhere here. No, so x coordinate we already calculated 2A by 3, y coordinate can be calculated in the same procedure, that is left to you as an exercise, and the value for y coordinate is b by 3. For x coordinate 2A by 3, for y coordinate b by 3, this we did not work out, it's left to you to work out. Now, let us try to calculate center of mass for 3-dimensional object. So far, we have calculated center of mass for 1-dimensional object as well as for 2-dimensional object. Let us try to calculate center of mass for a 3-dimensional object, for example, a hemisphere. Let us choose a hemisphere here, where the center of mass of this hemisphere will be located. To calculate the center of mass of hemisphere, first you choose an element select the axis in the same way as you are selecting previously. So, the axis of symmetry for the hemisphere comes on the y axis. So, automatically x coordinate will be 0, z coordinate will be 0 because the center of mass will lie on the y axis. So, its x and z coordinates will be 0. So, only thing you have to find is y coordinate. To find that, what we have done, we have taken an element of thickness dy, radius of the hemisphere is r, let this distance is y, that means we have selected an element of thickness dy at a distance y from the origin. If this is origin, from origin at a distance y we have selected an element of thickness dy. As usual, you have to go for mass per, you have to go for dm first, mass of the element selected. So, this element has volume how much? Volume of the element dV is equal to area of the element into thickness. Area of the element is pi into, if radius is r, suppose radius of this is r, then area will be equal to pi r square into dy will be the volume. But let us eliminate this small r in terms of y, that would be equal to pi into r square minus y square. This r square is equal to r square minus y square dy. So, dV, volume of the element that we have selected, is equal to pi into r square minus y square into dy. Therefore, mass of the element that we have selected will be equal to density into volume, density into dV, which is equal to this, rho into pi into r square minus y square into dy. Now, y coordinate of center of mass as usual is equal to 1 by m integral y dm. We want y coordinate, no? So that's why we will use the formula for y coordinate of center of mass, which is equal to 1 by m into integral y dm, which is also equal to integral y dm by integral dm. These are same formulae. Now integral y dm means integral of y into this, y into rho into pi into r square minus y square dy divided by integral of rho into pi into r square minus y square into dy. Now what are the limits? We are integrating the function in terms of y, means limits of y are from 0 to r. Therefore 0 to r, 0 to r. These are the limits. Now let us try to integrate this. YCM is equal to rho gets cancelled, pi gets cancelled. What is left out is integral y into r square minus y square dy from 0 to r divided by integral r square minus y square dy from 0 to r. So if you integrate this, this will be, if you integrate this, YCM is equal to y into r square dy integral. See here you have two integrals. Y into y square means y into r square is one term, y into y square is another term. So what you will have is y r square dy integral minus y cube dy integral. So y r square dy will be equal to integral of r square y dy will be equal to r square into y square by 2 y into r square dy integral means y square by 2, limits are 0 to r minus y cube dy integral of y cube dy, that means y power 4 by 4, limits are 0 to r, divided by, here r square dy is one integral, r square dy means r square into y, limits are 0 to r minus y square dy, integral of y square dy is y cube by 3, limits are 0 to r. Now if you substitute the limits here, YCM will be equal to r square into r square, r power 4 by 2 minus, here also if you substitute the limits, r power 4 by 4 divided by, here if you substitute y equal to r cube minus, here r cube by 3. So here what we will have is r power 4 by 2 minus r power 4 by 4 equal to r power 4 by 4 divided by, this will be equal to 2r cube by 3, which is finally equal to y center of mass. Y center of mass is equal to r power 4 by 4 by 2r cube by 3 means r cube and this power 4 gets cancelled, 3r by 8. So this is the y coordinate of center of mass for the hemisphere. X coordinate is 0, XCM is 0, ZCM is 0, because we have chosen the axis of the sphere in that way only. So this is how we calculate center of mass for a hemisphere.